Testing. Okay. Hello? Boleh dengar tak? Mana yang lain Right. Okay, welcome back. Okay, 6. Ada lagi. Okay, 3 more students. Not in Who's here? Zamzame, Sadiq, Ain, Arif. Siapa yang user ni? Okay, okay. You boleh edit kat sini, tukar rename nama you kat sini. Nampak? Ni, edit rename. Rename your name lah. Okay. Oh, by the way, nanti boleh tak? This one kan, atasnya ada chat tau. Can you share me the uLearn link? I think I didn't get the uLearn link for MEKH. MEKH5133 ada uLearn link dengar tak?
Dengar. I think lecturer supposed to create a subject inside the uLearn.
Oh, okay. So, Dr. Fiza, did she create the uLearn link for that?
No, I don't think so.
Oh, okay. So, before this, she shared to you using email, the notes?
Usually lecturer gave us the link actually.
Link lah, okay. So, no uLearn, the uLearn itself for the subject, there's no uLearn. You didn't access anything yet?
Yes.
Okay, right. You guys macam confused gitu. Confused, especially those yang already from UTEM kan. I think you already know what's uLearn For those yang didn't graduate UTEM, like Zamzame Ain, it's different lah. But for those confused, so like uLearn, okay. 2 more students. Siapa tadi? Heba dengan siapa
Denny.
Oh, Denny.
Siapa?
Denny.
Denny. So 4 from UTEM 5 from UTEM.
5. Yes.
Okay. Korang ni satu rumah ke apa ni? Ni pergi panggil kawan ke apa? Arif.
Yeah. Panggil dia ni.
Pada tidur. Sleep already. Fall asleep. Heba, can somebody message her and then tell her that she can log in using the same password and ID. Okay? Everybody had lunch? Ready eaten?
Yes.
I didn't have my lunch yet. I had only breakfast this morning and then I just go and buy lunch but didn't feel like eating yet lah. Okay, so it's okay. After this I only eat lah 5 PM later on Okay, so while waiting, Denny, okay. Last person, Heba. Heba is staying with who?
She's alone.
Ain duduk dengan siapa?
Alone.
You are still alone with your family or
Yeah. Yeah, alone here in Melaka.
alone? Kesian dia. Tengok tu, kesian dia duduk kat living hall tu. Nampak tak? Okay, alright.
Okay.
Is in. Alright, welcome back everybody. So let's go to the second part. Okay. Second part of this class. So we are going to continue with the torsional spring element. Okay, torsional means that the rotational part of the spring element. So you have the spring, but you're going to rotate it. So according to the table just now, you have the spring. You can get the torque value is equivalent to the K of the spring times the angle. Okay. And then for this one is the common torsional springs constant. Supposedly, as you know, the normal equation is T equal to K theta. But for the case of coil spring is that you are using this equation. So KT is equal to E, the elasticity of the material, D to the power of 4, D is this diameter, over 64 N D. Okay, so this one is the common equation. Of course, you can try to derive it if you want, but no need lah, okay? Because we have lots of things to derive later when you do the dynamic system. And then for the case of hollow shaft, means that you have a shaft that is hollow inside, okay? You are given by this KT value, right? So where do you use this hollow shaft? Example, in a torsion bar suspension system. So you have the hollow shaft here, right? So next we go to the series and parallel spring element. Okay, so we are going through the first part, which is parallel spring element. So this one is we start with the modeling of spring. Okay, spring without the mass value, right? So you have force here. Okay, you're going to give the force, the spring force, and then the spring, there are two springs that is connected parallel. So you have spring with K1 and spring with K2. So the equivalent of this is that you have force and KE value, which is the equivalent value of this two spring. Okay. So note that if you see here, the parallel spring have the same deflection X. So either way, if you have two spring like this, okay, you're going to push it downward, you will have the same deflection of X. Okay. So it means that you can derive the X value as X equal to using the equation of F equal to Kx. So you would get X equal to F1 over K1, and which is equal to F2 over K2 because X is the same here. Okay. So if the system, we call it as a static equilibrium, then you have F equal to F1 plus F2. Okay, means that you have two force, which is the summation of F1 and F2. So you derive it here and then you get K1 plus K2 in bracket X. So therefore, you can actually calculate KE, which is K1 plus K2. Meaning that if you have two springs in parallel, you can actually directly calculate KE is actually K1 plus K2. So if you have three springs, 1, 2, 3, so means that KE equivalent is K1 plus K2 plus K3. So in contrast, if you have a series of spring elements, so you have two springs like this. Okay, so it's connected in series. Okay, you're going to push it like this. Okay, this one is fixed. Okay, you're going to push it, then means that the spring will actually deflect. Okay, it will be shortened, X. So here that note that series spring has the same force value. So no matter what, force given to these two springs is the same. Okay, so therefore we can actually write here X equivalent X A, which is for K1, plus XB, which is XB is for K2, is deflection. Assuming that XA and XB is not the same deflection. Okay, so if the system is in static equilibrium, so you can write out X equal to X1. What is XA? XA here is F, same F value, okay, over K1 plus XB value is this one, F over K2, right? So you organize it again, the equation, then you can get 1 over KE. Actually, the K value is 1 over KE equal to 1 over K1 plus 1 over K2. So meaning that for spring in series like this, you can actually get the equivalent equation by using this equation. Alright? Okay, so far okay, guys? Okay,
Yes.
because next we are going to do a simple exercise. Okay, next. Right? Now we start to take out a piece of paper. Okay, guys, take out a piece of paper. Okay, try. Okay, problem is determine the equivalent stiffness KE of the arrangement shown below. Okay, try to get what is the KE value, K equivalent. Right, I give you like 1 minute lah. 1 minute. Very simple. Use the previous equation. Use this equation and this equation. So means that you see that this is spring in series, right? This is spring in parallel. So settle first this part. Okay. Then after you get this part, you will get the K equivalent here. Then it become a series. Okay. So 5 minutes. 5 minutes. 1 minute only. Very easy. Okay. Okay, after you write that out, then later take out what your answer and put it like this. I want to see your answer. Okay, like this. So what's your answer? Okay, here, this. Okay. Let's see if you can get it correct. Okay, oh, finish. Arif dengan Kogen jangan tiru Copy better
Tak dapat apa, tak dapat.
Don't copy Well, below there I already give you the answer. So, did you get the answer?
Dia
Okay, anyone? Finish? Okay, did you get the answer?
Yes.
Again?
Not yet.
Hey, not yet. I already finished drawing in front.
But sorry, I can't see the whiteboard.
Oh, you cannot see?
No.
Is it too small? Can you, just now, this morning, okay, you click on my view, and then you double click on that. Double click
I
on
see
that.
it now.
Can you see
Okay,
it?
thank you. Yes.
Okay. All right. To make, because if you don't double click, then you will have a small screen of me, right? So double click that, then I will be the full scale. Right?
Okay.
So, Kuken?
Yes.
Kami?
Yeah, okay.
Arif?
Okay.
Shadik?
Okay.
Eba?
Yes.
Ain, dapat tak? Hanif? Hanif, I cannot hear you. Danny? I cannot hear you. Danny? Cannot hear you.
Madam.
Okay, alright. Anyway, tak apa. Okay, I will explain. Okay, so you look at, please double click on my face. I mean, you have the screen, right? My face there. Double click on that, then it will actually make it into a larger screen, which is the whole screen on your computer. Alright. So let me just explain this. So, okay, everyone.
Okay.
Okay.
I get it.
So, okay, let me just explain. So right now we have the spring. We have three spring in series and 2 spring in parallel. So what you need to do is that first, get these 2 spring first, the equivalent, KE. So what you need to do is that this is parallel spring, right? Use the equation KE, the first one, which is K plus K1, which is 2K. Right? What? And anyone? I heard a lot of voices. Anyone talking there?
No, just I'm in the library and there's many people
Oh,
here.
okay, in the library. Alright, okay. Alright. Okay, so first get the equivalent here, parallel. So you get KE here, which is 2K. So I draw this back again, K, 3K in series. And then you have this K equivalent here, 2K. Okay, now you can see that all this spring is in series. So by having that, you already know that based on the previous equation that 1 over KE is the summation of 1 over K. Okay, so this is the equation. So you have 1 over KE equal to 1 over K, 1 over K plus 1 over K plus 1 over 2K. So you get 7 over 2K. So this is the answer. Okay, so of course, if you want to get what is KE, then KE is 2K over 7. Alright, so everybody okay?
Okay.
Okay, alright, next is, we go to this one. Okay, determine the expression for the equivalent torsion spring constant for the step shaft shown below. So this is, you already learned before that in the previous slide, that even for a shaft, it's actually a spring. Okay, so it's a torsion. So find what is the value for the KT equivalent. Okay, for this one, just use the same method. So same method. This is easy. Here you have you have K and K. We take it as K1 and K2. Alright? So find what is KTE. Okay. 1 over this is it series or is it parallel?
Series.
Series is that the equation is 1 over
1 over
VE.
1 over KT1 plus 1 over KT.
T2.
So what do you get? KT
KT2
plus KT1 over K1 KT2. 1 over K. So the question was get KTE, right? So you get K1 KT2 over K2 plus KT1.
T1.
Alright? So you have proved that equation just now, answer.
Madam,
Yes?
Arif.
Keluar ni.
Dah boleh.
Keluar. Dah masuk dah?
Arif.
You
Dah.
enter again? Okay. Alright. So Arif, I think you already calculated it is at the back there. Okay.
Yes.
So next is we go to the modeling of mass and spring. Just now was only spring, So now we are going for mass and spring. So same table just now. So as you learned in previous last week class, you can actually represent the spring K force is equivalent to Kx.
Can I please see the solution in the whiteboard? Okay, just I need to write it down.
Okay, all right. Okay. Anyone else have any question? Best, not bad. What doing online class, Right. The best part is that I'm sitting. Okay. Hiba, okay? Finish?
No.
No? Which part you don't understand?
Wait a minute.
Oh, my writing is very bad.
Okay, done.
All right. Okay, so
Yes.
the table here is that it shows the value for f equal to q. For damper is that f equal to kx dot, which is the differentiation of the displacement. So it's actually f dx over dt. And then for mass is mx double dot, means that m dx squared over dt squared. Okay, so you can write it for easy derivation in the next slide is that we are going to use in this term. Yeah. So let's go to the first example of mass spring system. Okay, you have mass here. Okay, so first step is draw the free body diagram. You have M, you have the K value, right? M and K value. And then you have the force at this point, and X is the displacement on the mass value. Okay, so to actually write out the equation, the free body diagram of the equation is that you may write it as this value. M, look at this, M with displacement of xt, okay, which is this one, plus kx. So mx double dot plus kx, okay, equivalent to the force value, right? So you get the transfer function for this equation. Okay, everybody get it? Okay, this next is when you have the inclination of mass spring model on an inclination, which is you have a degree inclination with theta. Okay, so how you do this is that by actually writing out the equation again. So let's just do this example. Let me just write it out. So you have mass here. When you want to draw the free body diagram is that you have the M and then you have the spring. Okay, X value is the displacement and then you have the force here. Okay, so how you go by this is that start with the mass value. So M with the displacement of X, it refer to this table. So if you have mass with displacement of X, then you have mx double dot. Okay, so mx double dot, mx double dot plus, what else is connected to the mass?
Spring.
Spring, force.
Spring.
So K.
Force.
So K is, you have
Force.
given by this one. So Kx. Kx. Anything else? Any mechanical component connected to the mass? Nothing, eh? Okay. So this is the end of the equation on the left side. So equivalent to force value. Alright. So this is how you get the first equation here in this normal mass spring system, which is if it's in a horizontal plane like this. Okay. For the case of this mass is having a mass spring model with inclination. So if we have inclination, this is like this. Theta. We have mass here. Okay. Then you have the force going down. Okay. X. Then you have the spring. Okay. So this one compared to this, what's the difference? This one is that you have the degree.
Theta.
Theta, right? There. Okay, theta value. So first of all, similar to this one, get first what is the value on the left side. So let's say the value is starting with M value. So M X double dot, because you have the M with displacement X. So X double dot plus K X, okay, equivalent to what?
Force.
Equivalent to
Force. Force.
cos
Sin. Theta.
F M T sine theta.
Theta.
Okay, so that's why you have here, okay, you have here, and if you see here, theta S, if you look at this slide, for Fk force is Kx, and Fm, the mass is mg. So mg is actually mass times the gravity there. So but under inclined surface is that you have k theta equal to k delta st. Okay, for that part. So means that for this kx, okay, you have also k delta st here. Okay, and then for m theta you have m sin theta. So if you write this out again, you have mx double dot plus kx equivalent to this one plus you have k plus delta st x. Okay, and the m you have m x double dot plus md sine theta. It's not here. Okay, so that's why you get this equation, right? Next we go to the static deflection in mass spring Okay, now it's not in inclination, it's not in the horizontal, but it's in the vertical position. Okay, vertical position like this. So means that, oh, the wrong way. So you have spring, pause. Okay. So means that if you write this out using the same concept as the inclination just now, you have Fk equal to Kx, Mg equal to Mg, okay? And Fk theta is, as K theta means that the deflection due to the gravity there, okay? So you will get this value, Mx double dot equal to minus Kx plus theta St plus Mg. It's without the theta. Just now you have mg sin theta, so now it's only mg, right? So let's go to a real example of beam vibration. So you have two beam. You already learned about when you have two beam, fixed beam. Okay, it represents a spring. So this one can be drawn as this free model. So you have mass and you have spring underneath and connected to the fixed part here. Okay, so the K value for this beam is given by this, which is you have learned in the previous slide for the beam type, fixed beam type. So from here is that, okay, assume that the beam mass is negligible compared to M, okay, so that the beam can be modeled as a spring. So means that, of course, ideally in reality, the beam itself has a mass. But to represent this model is that we only take the mass of this M mass only. So the beam does not have any mass, but we represent it as a spring K. Okay? So determine the spring natural frequency of the oscillation. So you will know that when you have a beam, like when you drive on a flyover. So what happens is that you will feel vibration. Okay, vibration. So calculate what is the vibration, the oscillation of the system natural frequency. So from here is that, okay, you know that period of oscillation is 2 pi over omega n. So omega n, you can substitute inside here omega n of K over M. Okay, you get K value is from this, substitute here, then you will get omega n is this oscillation. Okay, so normally you will know what is the value of E, the modulus for the material, WH is the width and height, AL is the length of this beam. Okay, mass is this mass only, not including the mass of the beam. Okay, so from here you can calculate what is the natural frequency, omega n, right? Next, we go to the modeling of inertia of the rotation mechanics system. So similar to the linear system, okay, for the rotation system is that you have Fx, for linear is output is T, torque. So torque is given by K theta, so you can represent as this one. And for damper is that torque is equal to D, which is damping value, d theta over dt or F theta dot. And for inertia is that T equal to M theta double dot, right? So let's assume a torsional spring system just now. Okay, you have learned just now that when you have a mass, this is consider mass here, inertia. This is the spring. Okay, you have learned that if you have a rod, okay, it's actually represent a spring because it will actually rotate. Okay, so we have an inertia and then a spring connected to this one. So this is represented as this value. Okay, so find what is the T torque value. So KT value from here is that use the same concept when you model the linear model just now, when you have a mass and spring value. Okay, so T is equal to I theta dot plus K theta dot. okay, equal to torque. Right, how you get that is okay, you have a mass connected to the spring. So this one will be represented as the mass for inertia and connected. What? I heard voices just now. Anything? Anyone went out?
No, it's okay.
Okay, so you have this one inertia and this one is the spring. This is representative. Okay, so you have the torque. Find what is T. Okay, similar to the mass just now. Okay, what is, start with I value. So I theta, when you have torque, when you twist it, then you have a degree of angle. Okay, theta. So I theta double dot. So where can you use it? So you have inertia here. Inertia. So you have, oh sorry, this is wrong. I typed wrong. I theta dot. This is I. Not M. I. Okay, I theta dot. So you get I theta dot. What else is connected to the inertia? K value, K theta. So you see here you have K theta for spring value. Okay. And equivalent to the output. The output is the torque value. So equivalent to P. So that's why you get this equation. Right? So here is just to give the what is the frequency of omega n is given by kT over I. And this one is an example of cylinder on an incline. So it's similar to what I explained just now. When you have a mass system, a linear system on inclined motion, then you can actually get the equation as this one. Okay, so you have the md sin theta at this part, and then you have md cos theta at this part, moving to this part. So that's why when you write out the differential equation, you can get this equation. Okay, you just try this at home and try to derive it. Because I need to speed up a bit. If not, we don't have time. Okay, next, let's go to this slide, slide 36. Okay, slide 36. Okay, there's a correction to the slide. Okay, correction to the slide is at this part. And this part. I forgot the arrow part. Okay, so please edit in your slide. Actually, to get F value is x1 minus y. So let's just do this example. Okay. Equation of one mass, you already derived it just now. So we have one mass, you have a spring, then get what is the equation. So now we are going to calculate when you have one mass and you have two springs at each end here. K1 and K2. So let's do this example. So a practical application okay, of this example, imagine that you have a cam and follower in your engine. Okay, in the combustion system, right? Cam and follower. What happens that when the cam is rolling, then this one, this K1 will be displacing, and then combustion engine, okay, giving actually the engine will be combustion, will produce a combustion system here. So we are going to derive the transfer function for this system. So you have mass. One mass. Oh, I have to take this one. Can you see this? Yes. I'm not sure if you can see it. This. Boleh nampak?
Boleh.
Okay, this one is the example here. Okay, we have one mass, we have K1 and K2. K1 is connected to this end, and then this one is actually the cam and follower. So this K1 is actually having a displacement of Y, and this mass is having its own displacement of x. So find the transfer function. So we start with the same concept of when you have one mass and one spring value. So start with m. Okay, m. What is connected? What displacement is connected to it? So which is x. So you can write it as m x double dot plus what else is connected to m? K1 and K2, right? We have K1 plus K1 x. K1 is connected to x also. Is that if we have the displacement, K1 will also displace plus K2. K2 x. Okay? Equivalent to, and normally what you have here is you have the force value, right? But force value here does not, we don't have any force value. Force is 0. So we have 0 plus, okay, look at this system. Okay, after you have, because you have two displacement here, you have x and y. So y displacement will be the force part here. Okay, so we have K1 y. So if you rearrange this, okay, you have mx dot. Okay, in the equation is that it writes K1, rearrange it, bring this Ky here. So you have K1 x minus 1 plus K2 x equal to 0. Okay, so this is the transfer function for this system. Okay, everybody follow?
Yes.
Yes. Okay. Let's do this very quick. I only have 5 minutes before the time is up because 40 minutes already passed. Okay. So next is 2 mass and K1, K2. We have x value, x1, x2. Okay, so find, verify the equation of motion, get the equation. Okay, so I give you 5 minutes. 5 minutes to do this. Okay, while you do that, I'm going to end this meeting at 10 minutes. We will come back again with the discussion. Okay, try to do this.